The first speaker is Anna, which we talk about hot Milky Way halo seen in a 1 megasecond Chandra HETG observation of NGC 4051 over 8 years. It's a beautiful data set, by the way. The power of observing consistent Bayesian framework.
That this gas is really important for galaxies. Basically, where the baryons are deposited to accrete into the galaxy or to be ejected out of the galaxy. Okay. Ooh, rocky start. In particular, CGM of Milky Way like galaxies is very, very interesting. Why is that? Well, when we look at this figure we probably saw many times, the fraction of the baryons that were converted into stars, we see that on low mass end and the high mass end, those baryon transformation into stars is highly suppressed, we think by stellar and AGN processes. And then turnover point between the stellar and AGN processes is exactly at this Milky Way kind of halo mass scale. So that makes it very, very interesting. And of course, Milky Way is very close, we live in it. So it's also the easiest halo to study. So let's see what we can learn about Milky Way halo and also galaxy evolution. So we could study it in a mission, and it has been observed by low resolution CCD detectors already for some decades. And I show here the two most recent such emission spectra from HaloSat and eROSITA teams, so from CCD detector and a silicon drift detector. And apart from the fact that these spectra are low resolution, this kind of approach also necessarily collects data from very large regions on the sky because the Milky Way emission is actually very, very dim. And then typically these spectra are fitted with kind of two thermal component models, the local hot bubble and then the extended halo. But we can also study this halo in absorption. And this is because, as I show in this cartoon here, the hot halo surrounds us everywhere. So basically, there is a gas between us and any, especially extragalactic source. So it's very easy to do it in absorption. And why would you want to do it in absorption? So first of all, since it's a point source, we would look at the point source, absorption towards the point source. We can use the gratings we all have been talking about and get high resolution spectra, right? High resolution means more physics. So we can get much more information than from a CCD spectrum. And it also means we can probe smaller scales. And also because this halo is present everywhere, we can do this all over the sky. So why would that be important? Well, because as shown here on the cartoon I borrowed from the eROSITA paper, there's a lot of hot gas apart from the halo that could be absorbing, like the local hot bubble, super bubbles, galactic fountains, chimneys, other things. So you really want to map it all across the sky. So what has been done so far? Well, we've already gained a lot of understanding of the Milky Way hot halo by studying absorption towards featureless blazars. And you will hear actually some of the highlights, I think, in the session later. Unfortunately, these kinds of satellites are limited in number because there's fewer objects like that, and also because you need very deep exposures, and it's just hard to get those kinds of observations to build really large samples that will span the whole sky. But we also have a lot of radiatively efficient X-ray bright AGN. So, but these are not often used for Milky Way absorption, even though, you know, they span the whole sky. So you could, and we have lots of those kinds of observations in the archive. So you could really probe the Milky Way everywhere. And why is that? It's basically because these AGN have their own intrinsic absorption. There's a whole session about that this afternoon, right? So to study the Milky Way absorption, on top of that, you really have to be sure you can disentangle the Milky Way absorption from the AGN absorption towards an X-ray bright point source. So let's take this problem and see if we can do something good about it so that we can take full advantage of these, you know, many deep grading spectra of AGN that we have in the XMM and Chandra archives. So we constructed an approach and to tackle this problem, and the first ingredient of our approach is the self-consistent treatment of absorption. So sometimes some studies focus on only individual lines, but in deeper spectra, grading spectra, you know, even having few weaker features gives you basically comparable statistical power to having, you know, a one bright feature. And also importantly, we never fix any parameters. So, you know, the AGN and the Milky Way models can, you know, have whatever covariances and errors they want. That's very critical. And then the second ingredient is using a Bayesian framework that we build on Monte Carlo Markov chains and deviance information criterion. So this ensures first that we achieve the global best fit, even when our models have lots of observers on them, lots of parameters that can be hard to achieve with simple optimization models. But also, this kind of framework provides robust model selection. So specifically, we can agnostically test different observers at each step, such as, for example, an AGN observer and a collisionally ionized observer, and ask which one is more likely given the data. So this way we build the correct model that comes out of the data and not what we think the model should be. And this is what happens when we combine the two ingredients. We can clearly separate the absorption by the Milky Way from the absorption in AGN. Here I show the approach applied to 700 kiloseconds of NGC 4051 data, with black line showing the global fit that includes the wind from the AGN, and the red line just singles out the whole Milky Way halo absorption. Of course, the data set spans many angstroms. And while I highlighted certain lines, I will just re-emphasize here that the statistical signal comes not just from those clearly visible lines, but also from many smaller features. So now, also something new in our approach to extract new information from these data. Since people have done similar things in the past, we added a third ingredient into our analysis, and this is the photoionization by the cosmic background, okay? So most studies of the hot halo of the Milky Way interpret this kind of data under the assumption of collisional ionization equilibrium. However, we know that if the gas has low enough density, then even such a weak field as the cosmic background can provide photoionization and be important. And we also are sure that the cosmic background is here. So let's see how it could potentially affect spectral signatures. So here I show ionic fractions for oxygen 7 and oxygen 8 that have a lot of features in a typical Milky Way hot halo absorption spectrum. And dashed lines show their ionic fractions for collisionally ionized model. And now let's see what happens if we add cosmic background as seen in the local universe. So we see that these ionic fractions change substantially and are completely different than the collisional ionization fractions, which means you'll see different features at different temperatures. And this starts to be important at densities below 10 to the -3 already. So this is huge, right? Like we're used to seeing 07 or 8 and being like, okay, this is a million Kelvin gas, but that's not necessarily true. You have to stop and think, what is the density of my gas actually, okay? Of course, cosmic background doesn't just affect oxygen. There's many other ions that in the spectra as well. So we are using all of them, right? This is very important. So these are, for example, less affected by the photoionization by the cosmic background. So again, you want to explain all of your data, all of your features with one model and not just analyze them one by one. Okay, so let's see what we can see about the properties of the hot halo of the Milky Way and how do these measurements compare to typically assumed collisional ionization. So we see, we show the physically correct measurements in red, the one that include the photoionization by the cosmic background, and the collisional ones for comparison in blue. and we see we get the typical temperature of the virilis Milky Halo mass. We do not detect a second temperature component, which is seen in some other work. We have a halo that's consistent with being stationary, but uncertainties on velocity are large. We get typically measured column densities and also line widths. So you may ask, things kind of look the same for the two cases. Why did we bother with more complicated model? Well, for example, not everything is the same, okay? So here we see that we look at metallicities, and we see that the model that includes photoionization by the cosmic background strongly prefers lower metallicities, while the collisionally ionized prefers higher metallicities. This is seen in our work and also other results as well. So this is one important result that personally gives me a pause. And then a second big difference with respect to the collisional models, we saw that those ionic abundances change as a function of density, right, of the hot halo. So can our model constrain this critical parameter? And it looks like yes. The most probable density is about 10 to the minus 5, meaning that the collisional assumption most likely does not apply, at least in the sideline towards 4051. And it also lets us measure the gas directly in principle. Uncertainties are large, and as discussed, but as we've discussed, there are many deep data sets, and we're gonna even have more. We're gonna have better collecting area instruments. So I am very excited for this kind of approach to studying Milky Way hot halo. Just to quickly summarize, I showed you how we can use the deep spectra towards AGN that might be complicated, but are very deep, very common, very plentiful in the archive, by using self-consistent modeling, Bayesian approach for model selection, and inclusion of the cosmic background photoionization. And this gives us new insights about metallicities and potentially densities, especially when we get higher statistics data sets. So we'll apply this method to archive, to CRISM, and yay, CRISM's launching very soon. But if you're excited about studying Milky Way halo, there's something better that some speakers already talked about. The kind of instrument we actually need is wide field of view microcalorimeter to really map the emission everywhere on the sky. So line emission mapper is that kind of instrument with 1 eV resolution in the center, but also something that has not been mentioned yet, an all-sky survey at high spectral resolution. Guys, like, that is so exciting. Just high resolution X-ray spectrum anywhere you look on the sky, okay? Amazing. So that's a part of our proposed program. And we'll talk more about LEM in the session tomorrow evening. But if you have any questions about LEM, just let me know and I'll stop here. Thank you very much.
Thank you, Anna. Questions for Anna?
Hi. So the systemic velocity of NGC 4051 is like 600 kilometers per second.
Yes.
So how do you know this is like not a blue shifted outflowing gas and not Milky Way's halo?
It's consistent between the two epochs. It's consistent with redshift 0. It's consistent in terms of NH with Milky Way. So it's very unlikely that it is the AGN absorption, basically. And it's also, we basically, and I think, sorry, I should have maybe step back. You take the photoionization by the AGN to construct a wind model, and you can get a fit that kind of tries to explain some of this feature. And then you have your Milky Way model, and then you ask the data, which one is more likely given the data, and the Milky Way model is much more, like orders of magnitude more preferred. Okay, so the critical step here is the statistical model comparison, and this is not just looking at CSTAT and seeing, oh, which one is lower. It's actually using a statistic that is appropriate to your data.
Good, thanks.
Are there more questions?
So have you implemented the fault function for the absorption line?
But you wouldn't, I don't think you would see it with the...
No, actually, because the velocity is actually important, because saturation will affect saturation. Even you don't resolve the line, actually the fault function will let you to include velocity dispersion which then you can use line ratio actually to constrain the turbulent velocity of the absorbing gas.
So we measure blindness. I don't think you would be able to statistically distinguish void from Gaussian for this.
No. You don't resolve because the Ford function will let you to handle saturation of absorption.
Okay, I don't think these are.
Yeah.
Looking at the transmittance of these observers, I don't think any of the lines are saturated.
No. See, like oxygen 7.
Yes.
Resonance line is saturated for our hot gas in our galaxy. So then you use like a beta versus alpha.
Yeah.
You can.
So to my understanding, the model does take into account the saturation. I will double check though. I was not under the impression that they were saturated, but I'll double check. Okay.
Thank you, Anna, again. Time to move on. Next speaker. Next speaker is Chandra X-ray from Stanford University. We'll speak about constraining the chemistry, turbulence, and more in the multi-phase hot circumgalactic medium.
Am I audible correctly? Okay, I'm just touching this. Okay. Hello, everyone. I am a postdoctoral fellow at KIPAC Stanford University. I work on different phases of the circumgalactic medium of the Milky Way and also other nearby Milky Way-like galaxies. But in this talk, I'm going to focus on the hot circumgalactic medium of the Milky Way, probed in X-ray absorption. But I'm happy to talk about the other aspects if anyone is interested after the talk. So probably in all the CGM talks, you will be seeing the same picture, which shows why the CGM is multi-phase. I mean, everyone before me has already introduced what CGM is and why it is important, but I'll also briefly mention why it is important in the context of my talk. So CGM is slightly different from the ISM and the IGM in the sense that it is spatially different. It is the multiphase gas that surrounds the stellar disk and interstellar medium of a galaxy and is expected to be extended out to the virial radius. It is not as dense as the ISM, but it is denser than the IGM. And it has like a lot of things happening there. There are accreting gas coming in. There are also outflows. And also there are recycling gas, which has intermediate temperatures. And most of the work in the last two and a half decades has been done in UV, which probes the cool gas. But most of the massive and volume filling component is actually in the hot CGM, and hot and cool are very subjective in this context. So in a moment, I'll say what hot exactly means. And for galaxies like Milky Way or Milky Way like other galaxies, there are primarily two sources of this hot CGM. One is the infalling gas from the IGM, which is shock heated, and that has comparatively lower metallicity. And the other source is the denser, hotter, and metal-rich CGM. So what we actually see is the mix of these two contrasting properties. And depending on what exactly happening, depending on the heating, cooling, and mixing, we can have different physical and chemical properties of the hot CGM. And I will also briefly mention that CGM should ideally be called intragalactic, just like we say intracluster or intragroup. So the term CGM actually comes from the optical perspective of the galaxies. But we will still stick to the CGM because intragalactic medium is going to have a complicated acronym. So there are two different ways you can observe the hot CGM, and people have already explained what those techniques are. In case of emission, we can observe both the continuum and the metal line emissions, while in case of absorption, since we do not have any hydrogen line, it is only the metal lines where we can, probe the different relative abundance ratios. And in this context, we are primarily going to focus on the two inertial transitions of K alpha and K beta. And as Daniel mentioned that since K alpha lines are often saturated, we need the K beta lines. So since I work on both emission and absorption, I'm kind of have a diplomatic take on which one I should talk about. But in the context of this talk, I'm going to focus on the limitations of emission and the pros of absorption, but they are really complementary to each other. So what we actually need is a combination of emission and absorption. So the thing is, in emission, one of the measurable quantities is emission measure, which is proportional to density square, which means it's biased to the denser gas. And in general, we expect the denser gas to be closer to the galaxy. So we are most likely to probe the extraplanar or the inner CGM, while in case of absorption, we can probe both the denser and the less dense gas. The other bias in emission is that it depends on the emissivity of the particular metal line. And for example, in case of oxygen 7, we already know that its emissivity peaks somewhere around 10 to the power 6.3 and sharply drops in both sides. So we are biased to measure that temperature in emission, while in absorption, it primarily depends only on the ionization fraction, which means it allows us to probe a broader range of temperature. So if we combine these two things, density and emissivity biases, absorption allows us to probe a larger range of density and temperature, which means a larger range of phase parameter space. The other issue with emission is that the soft X-ray region, as all the LM people have already explained, it is rich with the foreground, like the solar wind charge exchange, as well as the local hot bubble. Even when we are observing the CGM of Milky Way, that is a problem. And when you're observing the external galaxies, that becomes even more complicated because the CGM of Milky Way becomes part of the foreground. On the other hand, in case of absorption, that is not much of a problem because the local hot bubble doesn't contribute much to the absorption. And also thanks to the grating, we can resolve the zero redshift lines from the other lines. So there we can not only resolve the different metals, we can also resolve different transitions of the same ion of the same metal, which we cannot do with the CCDs, at least currently. So for last 25-ish years, whatever has been done in case of the CGM of the Milky Way, the main tracers have been the helium-like and hydrogen-like ions of the oxygen, that is oxygen 7 and 8. And here people usually target the blazars because they have the clean continuum. And usually the blazars at higher galactic latitude usually be greater than 30 are chosen to avoid the contamination from the ISM as much as possible. And as you can see, the focuses are often on oxygen 7 K alpha, K beta, and the oxygen 8 K alpha. The oxygen 7 K alpha is the strongest line, but often as they are saturated, we need to combine their equivalent to it to get the saturation corrected column density, which is often significantly larger than the column density you get from the linear part of the curve of growth. And if you have also the oxygen 8 column density, which is slightly harder to get because you need a higher signal to noise spectrum, but there you can get the temperature of the gas from the column density ratios and get the ionization fraction corrected column density. Even though in a lot of studies, people have assumed the ionization fraction of oxygen 7 to be equal to 1, that is not always true. And the list of papers I'm mentioning, it is definitely not like the exhaustive list. There are many other works, but all of these works had agreed upon one thing, is that the temperature is consistent with the virial temperature of the Milky Way, and also the column density varies across the sky. So if you model it, it is pretty much consistent with a spherical halo. And if you combine it with emission studies, you can break the degeneracy between, density and the path length, and hence calculate the total mass. So the spatial extent is larger than 200 kiloparsec, and the mass is large enough to account for the missing galactic baryons. So everything is pretty much consistent with the theory. And if you are feeling very relieved right now, I'm going to take out the relief in a moment. So in all of these studies, the underlying assumption is that all of the oxygen 7 and all of the oxygen 8 are coming from the same phase. And also all the oxygen and metals are in solar-like chemical composition, which may or may not be true. So we try to test that if that is actually true. And for that, we use all other metals that we can probe. For example, carbon and nitrogen in the lighter side, and also neon, magnesium, and silicon in the other side. And we are primarily focusing on the helium-like and hydrogen-like ions. And for each of the metals, before doing the actual ionization modeling, we start with the model-independent analysis, where we first calculate the temperature corresponding to each metal. So from the column density ratio of the hydrogen-like and helium-like ion, we can calculate the temperature corresponding to each individual metal and see if they are consistent with each other. The next thing we do is now calculate the column density ratio of different hydrogen-like metals or different helium-like metals and see if they're consistent with each other. If they're consistent, that's great. That means we verify all the metals are indeed coming from the same temperature. And as a byproduct of this analysis, we can also test if it is a solar-like chemical composition because we have more than one metal. Now, while the principle looks very straightforward, one of the main challenges is that, well, there are several challenges, but all of these metals are less abundant than oxygen. In fact, that was the reason oxygen was used as the main tracer. So you need to have a really high signal-to-noise spectrum to analyze all of these metals together. And also, since these are very faint lines, it is challenging to have a global as well as a local continuum. So we start with a 1.8 megasecond spectrum toward the Blazer 1 is 1553. This sideline was primarily observed to study WIM, which probably Fabrizio will talk about. But any sideline also passes through the zero redshift, and we can look for all the lines we expect to see. So you can see that all of the lines like nitrogen, oxygen, they're there. But we also detect a neon 10 line, which was not expected. And we find that whatever we were trying to test, they are not consistent. The temperatures are not consistent. The column densities are all same, although we expect oxygen to be more abundant. So now we do a hybrid ionization column modeling, which is basically collisional plus photoionization modeling. And what we find is pretty much a series of surprises because one, in addition to the virial phase, there is a super-virial phase that is needed to explain all of these lines together. We find that oxygen 7 and 8 are not coming from the same phase, which means the previous baryon and metal content of the virial phase need to be revised if this is a ubiquitous property. And also we find that the neon to oxygen and nitrogen to oxygen, they are supersolar. There is an excess of nitrogen and neon or an underabundance of oxygen. And we also find that the solar model predicts a lot of strong iron lines, which are actually not there in the data, which means the gas could be alpha enhanced. And we continue to look toward other sidelines. For example, this is at L equal to 180. So this is pretty much away from the all the Fermi bubble and Rosetta bubble. And here we pretty much find the same thing, except that now we have a larger set of metals. And here we find, in addition to the virial and super-virial phase, we also have a sub-virial phase, which is usually found in UV, but here we have a better constraint. And the chemical compositions are more or less the same, that we have a non-solar chemical composition and also alpha enhancement. But here it is pretty much a bit more complicated because we don't see the same supersolar composition in all the phases. So there might also be inhomogeneous mixing as well. And this is some recent results, but I won't talk about the stacking here because the next talk is on that. But we also have evidence there. And we are continuing to look at other high signal to noise sightlines in the archive. And this is one of the recent findings which we will be submitting soon. Where we are finding pretty much the same thing, that coexisting super-virial and virial phase and also supersolar neon to oxygen. And I'll just briefly mention this thing where we are basically comparing the total line broadening with the thermal line broadening and trying to see if there is an excess, which indirectly tells us the presence of non-thermal line broadening. And this is just a small subset of the data, only maybe 10% of the data. And it would be interesting to see if this trend continues. So this is the summary. So one line summary is that the thermal, non-thermal, and chemical properties of the hot CGM, which is pretty much about everything of the hot CGM, they are yet to be understood. And this is only the CGM of the Milky Way. So when we go to external galaxies, our knowledge of the Milky Way will help us in two different ways. One is that how other Milky Way-like galaxies behave. And two, Milky Way is always going to be like, the omnipresent foreground in all the external observations. So understanding the phase structure of the Milky Way is going to help in that as well. So the summary is basically that going from just oxygen to multiple metals, we are finding that there are more than one phase. The chemical composition is different, and that is helping us to understand the past galactic outflows of the Milky Way. So the future X-ray missions should really look, since they're going to have a better spectral resolution, they will allow us to disentangle between the line broadening and line of sight velocities, and that would help us to better understand how the galactic outflows are impacting the CGM. So, yeah.
Thank you. We have time for one question.
Hi, Sanskriti, nice talk. You mentioned briefly that this result of the new super-virial phase has implications or revisions on the baryons content, and this was found exactly in the same lasers where the WIM was found. So could you briefly comment on the implications of this revision on the baryon contents?
Yes, sure. So the thing is, when the focus is only on oxygen, we have oxygen 7 and 8. And from their column density ratios, we find the ionization fraction of oxygen 7. And using that, you can get the total column density of oxygen. And using some assumption of metallicity, which is usually 1/3 solar, you get the total hydrogen column density. Now there, the assumption is all the oxygen 8 or 7 are coming from the same phase. But if they're not, for example, here we see oxygen 8 is coming from the hotter phase. So if we assume they are coming from the same phase, we will overestimate the temperature of virial phase, underestimate the ionization fraction, and that would increase the column density of total oxygen and total metals. So that way, the baryon content and the metal content of virial phase might be overestimated in oxygen-only analysis. But since the super-virial phase is there, that also has some non-zero mass and metal content. Now, depending on how ubiquitous that is, which we don't know yet, that will also have some non-zero baryon and metal mass. But again, the phase distribution will be different.
Let's thank again Sanskriti. Thanks for a lot. Next talk is remote and from Armando, José, Lara, Díaz, Infante on high resolution X-ray spectroscopy, a tool to unveil the super-virial hot component of the Milky Way circumgalactic medium. Armando?
Yes,
I hear you.
Can you hear me?
Yes, you can go.
Okay. So good morning, everyone. Thank you for this opportunity. My name is Armando Lara. I am a PhD candidate at the Institute of Astronomy in the National Autonomous University of Mexico, Mexico City. Today, I will present our recent study on the hot phase of the circumgalactic medium of the Milky Way using high resolution X-ray spectroscopy. So a lot of this has already been said, but let me repeat it anyway. To provide some context, let's begin with a general overview of a spiral galaxy. A typical spiral galaxy like the Milky Way consists of a visible disk with arms and a central bulge. Here I'm showing you a representation of the Milky Way with its bulge, bar in the center, and its arms extending around it. However, it's important to remember that around this structure there exists a halo of gas and dust. So let me define the circumgalactic medium, or CGM for short, as a gas around galaxies, being outside the galactic disk but inside its virial radius. So we know that CGM exists because it has been observed mainly in UV. It has been traced by elements such as ionized hydrogen and silicon-3, among others. And besides the detection of low ionization elements, other elements, including oxygen-6, for example, have also been observed. So studying the CGM is important for several reasons. Firstly, we need to understand how oxygen, which is produced in stars, ends up in the CGM. Secondly, the CGM is situated between the intergalactic medium and the galactic disk, so we expect a lot of material to pass through it. So this makes the CGM a large reservoir of material, which is crucial for understanding galactic formation and evolution. Furthermore, investigating the CGM could also help us to address the missing baryon and missing metal problem. So what's the missing problem? Maybe you already know, but let me repeat it, from Redshift 2 to nowadays, the amount of baryons observed at galactic scale is about 50% less than that predicted. So the lambda CDM model predicts that the baryon follow the gravitational potential of the dark matter halo, where they lose energy and cool and pull into the center of the halo, forming the galactic disk. However, the amount of baryons forming stars or scattering the interstellar medium is only a small fraction of the total number of baryons. So we expect in the galaxy. So it has been seen that in galaxies with luminosity less or near ejected star, the amount of mass expected lies around 2 times that we can observe. This plot here shows the fraction of baryons observed in galaxies within this mass range. So we see that in galaxies with these masses, only at most 20% of the baryons available in their halos have converted into stars. So what's happening? An hypothesis is that the missing baryons are still in the circumgalactic medium and have not finished falling yet into the disk. Another option is that they have already been accreted to the disk and then ejected into the halo. So as you can see, these possibilities involve the circumgalactic medium. Coupled with the missing baryon problem at galactic scales, we also find a missing metal problem. So from the number of stars we see and the star formation history, we can infer the amount of metals within the galaxy. This plot, again, here, well, shows the fraction of total metals produced that remain within galaxies. So as you can see, studies show that galaxies contain only 20% of metals ever produced. So what is thought is that the missing metals would have been expelled throughout outflows, for example, with explosions of supernovas and galactic winds. And that will carry all this material toward the CGM involving feedback processes. This, the bottom right figure presents a visual representation of a simulation of a galaxy with feedback. So you can see a galaxy in the center in which, when applying feedback, it throws oxygen-6 up to distances of hundreds of kiloparsecs. So this gradient, color gradient around the center, the distribution, so these way simulations have helped us to give possible answers to the presence of material around galaxies. So as you can see, study the CGM. It's important because it's directly linked to the formation and evolution of galaxies through all these processes. So this suggests that the CGM is a large reservoir of gas that can fuel future star formation within the galaxy, and also where the missing baryons and metals could reside. So the general idea, well, while the problem of the missing baryons is related to material falling out from outside the halo into the disk, the problem of missing metals is related to metals producing the disk and ejected out of it. So one possible scenario is that the shock heating processes during the galaxy formation has heated and ionized the gas, preventing it from falling into the galactic disk. And additionally, feedback processes might have expelled significant amount of material into the CGM. So as mentioned before, in this artistic representation, on the right side, we can observe gas accreting toward the disk through filaments and then outflow carrying this material away from the disk to the CGM. And moreover, this material can eventually be recycled, falling back into the disk. So simulations indicate that the CGM is a very hot and diffuse medium with temperatures near virial temperature of the galaxy. In the case of the Milky Way, approximately 1 million Kelvin. So what I have said so far is basically to show why material is expected to be in the CGM, why it's important to study. So as mentioned by Sanskriti, it's her work. So recent studies have shown that a large amount of mass is in the Milky Way in the 1 million Kelvin component, also called, I will call this component warm hot. And it's expected from simulations. However, in 2019 and 2021, Díaz and collaborators analyzed X-ray data using the CGM, studying the CGM of the Milky Way through 2 line of sights, Macarian 421 and 1ES1553 plus 113, and detected neon 10 and silicon 14. So these lines are related to a component above the real temperature of the galaxy, reaching temperatures greater than 10 million Kelvin, which I will be referring to as the hot component. Interestingly, this hotter component is not expected from theoretical models. So what these and other studies have revealed is that the CGM of the Milky Way is a complex multi-phase medium in which the non-expected super-virial gas phase coexists with cooler gas phases. And these findings raises many questions, such as how the gas reaches such high temperatures, or how this hot phase is distributed throughout the CGM of the Milky Way. So this hot phase has only been detected through a couple of individual sidelines. So we decided to explore its distribution. We investigated the hot phase of the CGM of the Milky Way using the stacking technique across different sidelines. So our aim was to only study the hot component. So we analyzed only the spectrum for 4 to 8 angstroms, where the silicon-14 appears, probing this gas. We use high resolution X-ray spectroscopy with LETG and HETG, which are the only instruments with good throughput below 12 angstroms. So in our data sample consisted of X-ray spectroscopy observations from quasars, Cipher-1 galaxies, and blazars. We excluded sidelines in which it was already detected and took out any target with absorption lines in the rest frame of the Milky Way. So we ensured that our lines were not contaminated with warm absorbers. So with this sample, we stacked the 46 HETG sidelines into one spectrum and the 9 LETG sidelines into another spectrum, resulting in 2 stacked spectra. The first was 11 megaseconds, while LETGs was 1 megasecond. So this significantly increases the signal to noise ratio. Here I show you our detections. These 4 panels show absorption lines modeled with Gaussian profiles on a local continuum. The first column is LETG data, and the second column is HETG data. So in black is the data, the red line is the model, and the blue line, okay, 3 minutes. Okay. And the blue line is the theoretical position of the line. So the gray shadow is the area where we let the model search for the line that we wanted to fit. So in the top two figures, what I'm showing is the absorption line of sulfur 16K alpha at redshift 0, and in the bottom panels is the silicon 14K alpha. So as you can see, these detections have high significance, and what's important of this detection is that these lines are producing the gas at more than 10 million Kelvin. So we are detecting the hot CGM of the Milky Way. So what do our results tell us? Well, we have confirmed the presence of the super-virial component in the CGM of the Milky Way. Our stacked spectra through different line of sight confirm that this hot component is spread throughout the halo. The gas is not predicted from simulation, so what could be heating it? Perhaps shot heating processes. This component is not confined to Fermi bubbles because our observations span multiple line of sight. So in conclusion, understanding the nature of this super-virial gas phase will significantly contribute to our comprehension of the CGM processes and their implications for galaxies. So as you can see, this topic is very interesting. There is still a lot of work to do, but for now, thank you for your attention.
Sure, Armando. We have plenty of time for questions.
For such a galactic absorption lines, you are looking through the interstellar medium. So I'm not sure why you necessarily include, say, based on simulation, there's no prediction for the hot gas. We know there's a lot of hot gas in the distant galaxy, supernova explosions, etc.
Sorry, I'm not getting the question very clear. I don't know with the microphone.
There's plenty of hot gas we know in the distant gas in the interstellar medium, which is due to the feedback from not necessarily from AGN, but from just supernova explosions, since supernova remnants we know very lot of hot gas, super bubbles. So I'm not sure why necessarily has to be a virialized halo.
Well, if I understand the question right, is why should we expect a halo of this hot with this hot component? So the audio was at the end very good, but in the first part it was noisy.
Don't you consider interstellar medium?
So
I actually answered this question if he doesn't.
I'm listening right clear now, but okay.
So all the sightlines we have chosen are at high galactic latitude, which means you have like a smaller cross-section with the ISM, first of all. Secondly, all the column densities are high enough. So if you consider like an ISM-like density, the path length is already larger than the ISM. So there has to be like, you know, gas in ISM as well as outside. Otherwise, you have to have an like oddly high density in the ISM. Yeah, that's what I'm saying. What we are seeing is ISM plus the CGM, but one, we have a high galactic latitude, and two, the column densities are large enough that it needs a like larger path length. So either you have an oddly high ISM density, which is not predicted, or you have a larger path length, which again is not consistent with the predictions. So yeah.
Because actually, I think Daniel's point is correct. I mean, these things go through the local group, through the CGM, and then through the disk. And now the CGM should in principle be virialized at a single temperature. There can be variation, of course. But if you see two components at such different temperature, I think the most reasonable interpretation is that you are passing through some supernova explosion or whatever. I mean, in the disk, there should be very hot gas in all galactic disks. So I don't think it's a unique interpretation. Let's put it in this way. I mean, in my opinion, a galactic origin is more likely. But
thank you. Any more questions? Okay, let's thank again Armando. And the last speaker is you, Fabrizio. I have to my paper, so for the title. It's Fabrizio with detection of the galaxy missing baryons in the CGM of 3 L-star galaxies.
okay, thanks. If you wonder what the logo is, that is my soccer team, Roma, and it's only on the first slide, unfortunately. Okay, so you have listened several talks on the Milky Way, the search for the Milky Way's missing baryons, which is where all these originated, and it's of course the easiest thing we can do because we are sitting in the Milky Way. So any line of sight from extragalactic sources will go through the several components in which we are seated in: local group, galactic disk, and CGM. So these studies of the CGM of the Milky Way, or of all these components, started actually more than 20 years ago. And there have been several talks before this highlighting the main results of these studies. The difficult part of the game is actually to find these CGM, but it's actually very important because as I said, any line of sight goes through all these components, and we are not really sure whether we are seeing the CGM, the disk, or and it has been actually very controversial in these 20 years. So the smoking gun is actually to see these baryons in external galaxies, these hot CGM in external galaxies. But this is very difficult, essentially because of it's difficult actually to find a signpost for these observations, and also the signal to noise, and these lines are very weak, so the signal to noise needed is very large. So what we did was to try, and I skip actually these slides because this is the problem of the missing baryons in galaxies. Baryons are really missing everywhere in the universe, but in galaxies, this is where you can see, I mean, compared to the expected baryon fractions, actually you recover the expected baryon fractions or only at the highest halo masses in groups, but I would say essentially in clusters of galaxies. But all galaxies from Milky Way down to dwarfs, they actually miss a very significant fractions of galaxy of mass, and the problem becomes more and more serious when you go to the low mass tail of this distribution. But this has been shown already. This is just a very rough sketch that shows you that the problem for galaxies is that essentially what we see in optical is only the disk of the galaxy, but then the galaxy, and it has been said already this morning, extend for at least 10 times the radius of galaxy disk, up to their virial radius, typically for a Milky Way like galaxies is 200 kiloparsec or so. And we know that there are several components in these of gas in this halo of galaxies. In particular, we know there is warmish gas with temperature below 10 to the 4 Kelvin, which has been seen in many studies in absorption in the far ultraviolet. These are only some of these studies. Essentially, what they do is the technique is always the same. They point a quasar in the background, and in this case, for example, they selected samples of galaxies. This is the quasar, and these are galaxies around the quasar, and they see absorption along the line of sight to the quasar. So they define the impact parameter to the galaxy, which is in this case 130 kiloparsec. The redshift of the galaxies, of course, they know, and so they have these absorbers seen mostly in low ionization metals and in H1. And often they also see associated to these absorbers hotter gas, temperature about 10 to the 5 Kelvin, which is seen through typically oxygen 6 or neon 8 in the far ultraviolet. So we know there is this, there are these clouds of green clouds in the cold AGM. What we decided to do was to actually use this cloud as signposts to look for X-ray absorption. So essentially, we selected a sample. These are the questions which we discussed already this morning. Well, first of all, I just showed you this. This is I think the best spectrum we have with this is the RGS, but also with Chandra, of the galactic component in our own Milky Way, and you clearly see all these different flavors in absorption, different temperature, from neutral material up to very highly ionized. This is only oxygen, and you see from oxygen 1 to oxygen 8. So there is really everything in the Milky Way. And we don't know exactly where it is located because these lines of sight go through all this material up to the local group medium, actually. So to go back to what we did, to try to see absorption in external galaxies, we selected a sample, which is the sample of this Lyman limit system. That's the way they are called. Those green small clouds in external galaxies, in external galaxy halos that have been seen in far ultraviolet. We used this as signpost, and we looked for X-ray observations in the archive, in the RGS and Chandra archives of these quasars that they used in the background. We found about, I think, 11 of these objects, but then, of course, we down selected in signal to noise because we need signal to noise in the continuum to see the lines. per-resolution element. And also, the other criterion we used was to for these Lyman limit system, we required that there was a clear galaxy association to the absorption system. And these actually yielded only these three sources. All three of them have RGS observations, and two of them, these two, have also Chandra LETG observations. These are the properties of the halos of the galaxies which are associated to these Lyman limit system absorbers, and these are the oxygen-6 absorbers which are associated with the Lyman limit systems. In all cases, in all the three cases, the Lyman limit systems are in photoionization equilibrium, photoionized by the external metagalactic field, but the oxygen-6 lines are not in agreement with, cannot be produced by the same gas. So there has to be another hotter component in these galaxies. In these CGMs. So these are the X-ray spectra, the 5 X-ray spectra, RGS and LETG, shifted to the redshift of the intervening galaxies. And we verified that in all of them, there was a hint of oxygen-7 line in this other redshift of the galaxies, or close to the redshift of the galaxies. Or consistent, I would say. The only one inconsistent is actually the LETG observation at less than 2 sigma. It's consistent at 2 sigma of these objects. These are the properties of the line. These are the significance in the single spectra, very low significance. But then if you fit the spectra simultaneously, this is what you get. These are the contours of line equivalent width versus position versus centroid of the lines with three methods. Essentially, this is by leaving the parameter free to vary in all spectra, and this is by linking the equivalent width in the sources in the two RGS and LETG spectra of the two sources that have both. And this is by linking also the position in these two sources. And you get significance which go from 4.2 sigma to 5.6 sigma. If you stack together the spectra, this is what you get after, of course, blue shifting then to the redshift of the intervening galaxies. And those are the contours for the oxygen-7 K alpha and K beta lines that you get for these lines. And the significance in the stacked spectra are 6.8 sigma and 4.7 sigma. This is, if you ask me what is the difference between these two panels, I will tell you, but I don't have time to go into the detail now. So what we did was to, based on the equivalent width that we measured in the stacked spectrum, we averaged together the properties of the halos. And the first thing we did was to measure the since we have K alpha and K beta, we could get a column density of oxygen-7, an upper limit on the oxygen-8, and this is the green line is the column density of the oxygen-6 seen in the far ultraviolet. And these are the regions that we constrain for the equivalent hydrogen column density and temperature of the absorber, and the virial temperature of the average halo of these three galaxies is about 10 to the 6 Kelvin. So it's fully consistent with the contours we have there. As I say, the temperature is between 5.8 and 6.3. All this is just to say actually that there is an inconsistency between the pressure of the cool components in the far ultraviolet and the hot components in the X-rays, which would require 10 times denser cloud in the cold clouds, which, by the way, would put the size of these clouds consistent to the size of the high velocity clouds in H1 that we have in the Milky Way. So I think when I say inconsistencies, I mean that the assumption should be, it would be nice if the two components would be in pressure equilibrium. And to close, what we did, having a measure of the equivalent hydrogen column density, we try to estimate the mass of the system, and the mass we get in terms of missing baryons in these systems is fully consistent with the total baryon component of the galaxies being in this hot CGM component. And this is the summary of the talk. Thanks.
Thank you, Fabrizio. Question? I have one.
Nice talk. I have a more general question, not so much about your derivation for the baryon content, but for the cold clumps in the CGM, am I right that their kinematics are dictated by the dark matter halos? So if you could get the width better, does that mean you could measure the mass in the dark matter? From the
Actually, these are observation of single lines of sight in absorption, so you don't get really clouds.
Oh, you don't have a, okay.
No, I mean, you see a single line of sight going through the halo,
Yeah.
You measure absorption there, and then you go to another galaxy, so you cannot put the things together. You have many measurements, but of different galaxies.
Okay.
It would be nice if you had more than one quasar sampling the same, in the background sampling the same galaxy, but it would be very, very difficult.
That's unusual, yeah,
Yes.
of course. So, okay, thanks.
Thank you.
Hi, Fabrizio, nice work. If eventually you stuck the signal, why do you impose a criterion on the minimal signal to noise per resolution element to select your sample?
No, I don't need that. So actually what we want to do is to see the lines in the signal spectra, because stacking is a very, very dangerous procedure. If you get, I mean, the hot halo has not to be there in all the lines of sight covered by, in which you see actually the warm component. So we really want to have a signal in the signal. Indeed, there was another source which there was a fourth source which actually had signal to noise per resolution element higher than our threshold, and in which we didn't see any hint for the line. Actually, there was a kind of a bump in emission at the position in which you expected it. And this is the only galaxy in all these samples of 30 objects by Prochaska and all these many samples, which has no clear galaxy association. The closest galaxy was at more than 2 megaparsecs, down to 0.1 L star. So you didn't see any galaxy at the redshift of the absorber, which to me means that is probably an intervening Lyman alpha absorber and not a halo absorber. And in fact, that galaxy was actually then eliminated by the sample of Lyman limit system. So yes, essentially we want to be sure there is at least a hint of the X-ray spectra are consistent with absorption depth. Yes.
Thank you, Fabrizio. Let's thank Fabrizio again.